Hi,
They
Alex. I didn't think you were coming today.
they canceled it last minute.
Ah, I told
Yeah,
you that if you didn't come, you were going to be half the class. Well, it looks like you're the only class member today.
I
So
thought we were doing galvanic
so close.
cells.
I was so close. Yeah, I don't know if I need to take this as a compliment or an insult. It's hard to say. That a compliment because people think, oh, they've got plenty of resources. They don't need to come to class. Or an insult in that they can't be bothered. I don't know. So I don't know. But anyway, if anybody wants to give me any feedback after watching this, then you can let me know.
Okay.
All right. Let's have a look at the syllabus here and get an idea of our timelines. All
Don't we
right.
have tests? Not this Monday, the next Monday.
I'm just going to cover that now. So we're looking at, let's see. Oh, Ronald's here. Okay. Double the class. Right, so we just did Discovery Day. Discovery Day, you all had a day off. Hope it was a nice day off. Well, Jack's here too. Oh, all right. So we're going to do the direction of galvanic cell problems today. And essentially, really the whole of next week will be a review, really. And then the test will be due on November 10th. And that's not to say that you have to wait till November 10th to do it. The extra credit will all close on November 9th at 11:59 p.m. But there won't be any real excuses. We're going to finish the material today, so there's going to be plenty of time for people to study. Not that would mean that people should wait until the last minute to study, because there's still a lot of problems here, still a lot of things to go over for you. I mean, once you've a lot of review for you to do, a lot of times for you to practice that test, and that should be your focus. Practicing the practice test over the next 10 days, and then hopefully during that 10-day period taking the real test. All right, so let's see where we're at here. Yeah, we're well ahead of the curve here on the content. So what are we going to look at today? Well, we're looking at this kind of problem here, or what I'm calling a direction of flow problem. So in this kind of problem, you're given a galvanic cell, and the galvanic cell has 2 electrodes in it. Those electrodes are solid metal. And here, if you're looking at the key here, W is copper. So copper is this electrode here. And lead is the other electrode, Z. So that's this one right here. The electrodes are joined by a wire. That wire is going to be designed to carry electrons through it. And those electrons could do some sort of work, possibly. The electrodes themselves are in a solution of a cation of the actual electrode. So the copper is in a solution of copper nitrate, and the lead is in a solution of lead nitrate. So what that means is the copper is in the solution of copper 2+, and the lead is in a solution of lead 2+. Now, back when I started going through this of galvanic cell stuff, I showed you the difference between something that was solid and something that was solid and something that was aqueous. And I'm hoping that that's something you're still down with. The other thing we see joining these 2 cells is a salt bridge, and the purpose of the salt bridge here is to act as a conduit for nitrate ions from one side of the cell to the other to balance out the electrons that are going to go through the wire. So you'll see that as we do this. So each of these letters here represents something. And down here, we've got different questions that are going to be asked regarding the cell. So the questions that will be asked, the direction of electron flow, that's going to correspond to a letter. a letter that's on that diagram. The direction of flow of nitrate, that will correspond to a letter as well. Copper 2+, lead 2+, species being reduced, species being oxidized, reducing agent, oxidizing agent, and the anode and cathode. So all of those things will have a letter associated with them, a letter that's on that diagram. Does anybody have any questions so far? All right, so look at the question that's being asked here. It says, consider the cell below. Please note that this cell may or may not obey the conventions of the standard cell diagram. Also, it says, assume the cell is working spontaneously and is working under standard conditions. Okay, so let me explain what I mean by this cell may or may not obey the conventions of the standard cell diagram. A standard cell diagram, if we go back and take a look at them, let's have a look. Just going back here, this is a standard cell diagram you're seeing here. And what we agreed about the standard cell diagrams is that whatever was on the left side of the double line here, which is a salt bridge, is going to be the anode. So always in a standard cell, the anode is on the left and the cathode's on the right. Then that doesn't vary because that is a convention. It's a convention that we all agree on. Now what I'm saying here in this diagram is that the anode doesn't have to be on the left. It could be on the left or it could be on the right. That's all it means. That's all it means. Now, the other important point about this statement here, assume the cell is working spontaneously. So what that means is it's working in a direction that allows for current or electrons to flow through that wire. So that's what it means. That's all it means. That it's working and the electrons are flowing through a wire from one side to another. The other thing that implies is that the E0 cell, of course, is positive. So we have to arrange the cell here to make sure that our E0 cell has a positive value. All right, so let's see how we proceed with this kind of problem, because these are the questions we're going to have to answer. The first thing you need to do is use the reduction potential tables to see which way the reaction is going to go under spontaneous conditions. In other words, we need to arrange this so that we end up with a positive E0 cell value. So going to if we go to the if we go to the reduction potential table, which I will pull up in a second. See if I've got it here. No. No. Nope. All right. Let's go take a look at the reduction potential table. It'll let me. All right. So there's the reduction potentials table. You'll notice they're all reductions, which means that when we're looking for the equations, we have to recognize that we are just dealing with reductions from the outset. Hang on, let me get back to. So I already did have that. Okay. Here we are. So this would be what we would have picked up off the reduction potential table exactly, would have been this. and lead 2+ plus 2 electrons. Okay, that's positive 0.340 volts, and the other one is negative 0.125. Now these are both reductions, as you can see here, but in a standard galvanic cell, one of these is going to have to be an oxidation, so we have to flip one of them. So the idea will be that we have to flip the one that will allow for the E0 cell, that is the sum of these, to be a positive value. So I've got both possibilities here, as you can see. So in the top one, this is what happens if we flip the copper. So we take the copper, says Cu, gives Cu2 plus 2 electrons, and then we reverse the sign of the E0. That comes out to be negative 0.340. So it should be clear to you that if we flip the copper, the E0 cell will be a negative value. So that's not going to be what we're looking for. However, if we take the lead and we flip the lead, you'll see that the E0 becomes positive 0.125. We add it to the positive 0.340 and we end up with a positive E0 cell value. So we know now that it's going to be the lead that needs to be flipped. As a rule of thumb, it's pretty easy. You look at the standard reduction potentials that you have off the table, and you choose the one that has the smallest numerical value. I'm talking about negatives, positives, or whatever. Choose the smaller voltage. And that's the one you flip. You always have to flip one. You can't get away with not flipping one. You always have to flip one. Does anybody have any questions?
Do they both have to be positive?
No, just the sum. The sum of it has to be positive. And sometimes they won't be both positive, Alex. Does anybody have any other questions about this? They just have to, the sum just have to add up to be plus after you flip one, right? Okay. I'm going to rewrite what I'm seeing there. Cu2 plus 2 electrons. So that stays as a reduction. And then we've got lead. And then we can write out a full equation here as well. So the E0 here, or E0 cell, is positive. That's all we're interested in. I don't really care what the actual value is. All I want to know is the E0 cell is positive. Then I can write some notes on here about what I know. Now, the whole point of a galvanic cell is something gives electrons to something else, and that something else accepts them. So what's happening here is the lead is giving up the electrons. And these 2 electrons that the lead is giving up, which I'm going to point to here, are the same 2 electrons that the copper is accepting. I'll say that again. The electrons that the lead is giving up is exactly the same as the electrons that the copper is accepting. And if you can accept that statement, it makes life a whole lot easier. All right, so I'm going to write a few notes on each of these because it's going to help me answer those questions that I was posing earlier. First thing, the copper reaction, because the electrons are on the reactant side. Remember, we didn't flip this one. It has remained a reduction. So it is a reduction that we're dealing with the copper. The other thing that we know is that it's plating. And the other thing that's related to that, because it's the anode, it is going to be, well, because there is reduction occurring there. Sorry, it's the cathode, I should say, sorry. Reduction occurs at the cathode. All right, so let's go back. Well, actually, I'll do the other things here before I do that. So this is oxidation because the electrons are on the product side. It's dissolving. And it's the anode. So let's go back to the cell diagrams that I showed you at the very beginning of this. Here we go. And if you'll remember, when we looked at the zinc and copper situation, you'll see that the zinc is dissolving. The zinc is turning actually into zinc 2+. And you'll see the copper here is actually plating. So there's copper 2+ ions in the solution becoming copper solid and plating onto that electrode. In this instance, the anode is the one where it's dissolving. It's the one that's giving up the electrons. The one that's accepting electrons is plating. Does anybody have any questions? All right, so all those things kind of help when I'm trying to answer these questions that are being posed over here. So the first one is the direction of electron flow. Now, what I would want you to see here is that the electrons are going to flow through the wire. So the answer can only be A or B in this instance. What we know is that the electrons are being accepted by the copper and given up by the lead. So the lead is on the right-hand side, which means it's giving up the electrons, and the copper is accepting them, which means that the direction of flow is going to be A for the electrons. Does anybody have any questions? The nitrate. Now the nitrate is going to flow through the salt bridge. Now the reason that the nitrate is relevant here is because what's going on is that the copper 2+ is becoming copper solid. The copper 2+ needs nitrate ions associated with it in order to balance out the 2+ charge. Likewise, lead doesn't need nitrates, but lead 2+ does need nitrates. So what's happening here is that the copper 2+ is disappearing. It's becoming copper solid. So it doesn't need nitrates anymore. But lead is becoming lead 2+, so that does need nitrates. So what's going to happen is that nitrates are going to flow through the salt bridge from the copper side over to the lead side. Now look at the charge on nitrate. Nitrate has a -1 charge, it's NO3-. So it stands to reason that it's always going to flow in the opposite direction to the electrons. We know the electrons are traveling via direction A, so we know that the nitrates have to flow via direction D. But the reasoning behind it is the fact that the copper 2+ doesn't need nitrates anymore, and the lead 2+ does. Does anybody have any questions? You're all okay with them? All right. The direction of flow of copper 2+. All right, so as I said, copper 2+ is plating. Now, copper 2+ is over here on the left side of the reaction. So what it's going to be doing is it's going to be traveling, it's either going to be E or F here. If it's plating, it'll be direction E. If it's dissolving, it'll be direction F. As it turns out, the copper is plating. As I've got here in my notes, it's going from copper 2+ to copper solid. Remember, if it doesn't have a charge on it, it's solid. So I know that the direction here is going to have to be E for the copper 2+. For the lead, we know the lead is dissolving, so the Pb is becoming Pb2+. And that means that we're dealing with direction H. So we're on this side over here. Does anybody have any questions so far? All right, the species being reduced. The species being reduced is going to be the copper 2+, because we've already agreed this is a reduction. So the copper 2+ is becoming copper. The other way of looking at it is that the charge on copper, which is 2, is going down to 0. That's a reduction. The charge on lead is 0 and it becomes 2. That's an oxidation. So that's a reduction that we're dealing with. And this is an oxidation. Does anybody have any questions? So the species being reduced is X, which is copper 2+, because copper is in a solution of X. So copper 2+ being reduced. The species being oxidized is the lead. The lead is going from 0 to lead 2+. It's dissolving. So the species being oxidized is Z, the lead itself. See, that's often an area where people make mistakes. Does anybody have any questions? So the next two are kind of the harder ones to deal with, the reducing agent and the oxidizing agent. When I use the word agent, it's in the sense of cause of. So we've already agreed that the species being reduced is copper 2+. But what's causing that reduction? Well, what's causing that reduction is the fact that the copper 2+ is accepting electrons. Those electrons are coming from lead. Lead, Pb, is effectively the reducing agent, because it is giving the electrons to the copper 2+, which is being reduced. So the reducing agent is lead. Obviously, what's being reduced and the reducing agent can't be the same thing. Likewise, what's being oxidized and the oxidizing agent can't be the same thing. What you will find, though, is that they flip. So the species being reduced, X, the reducing agent is Z. The species being oxidized is Z, and the oxidizing agent is X. So let's look at the oxidizing agent. So what's causing the oxidation of lead? Now remember, lead is Z. So what's happening is that the fact that the copper 2+ is accepting electrons, that's what's causing the oxidation of the lead. That's what's causing the lead to turn into lead 2+, because the copper 2+ is accepting those electrons. So the oxidizing agent is the copper 2+. Does anybody have any questions? I know that can be confusing. That's the worst part of this. If you can understand that, though, you're golden.
I have one. How do you know, or how did you figure out the direction flow of Pb?
But from the
H?
So yes, from the fact that lead is turning into lead 2+. So the Pb, which is the electrode, is turning into Pb2+ ions, which are in solution. So it's not, if it was plating, it'd be G. If it's dissolving, it's H.
Okay, thank you.
Is that clear?
Yeah, that makes sense.
Okay. Now the anode and the cathode are the actual physical electrodes, the bits of metal stuck in the solution. In a battery sense, it's the positive and negative terminal. And you'll notice if you look at any AA battery or AAA battery or whatever, you'll always see there's a positive end and a negative end. You would have noticed this, obviously, if you'd ever put a battery into a device. You have to arrange it so the poles are set up the way they look in the pictures. Usually, you end up putting the negative on the spring and the positive goes on the flat part. So it's the same kind of deal here. So the electrodes are the actual physical parts that provide the flow of electrons, because they're the bits connected to the wire or whatever's going to end up closing that circuit. So in this instance, the anode is where, by definition, it's where oxidation occurs. Do you remember I had that mnemonic? Anode equals oxidation and cathode equals reduction. But the thing to remember is the anode and cathode are the actual bits of metal. So A and O, they're both vowels, and C and R, those are both consonants. So that's how we can remember what's going on at each electrode. So the anode is Z, that's where oxidation is occurring, that's lead. So on the lead side, that's where oxidation is occurring. The reduction is occurring on the copper side, but it's the copper itself that is the cathode. That's the electrode. Does anybody have any questions? So I guess this problem's pretty easy, isn't it? All you have to do is just remember A, D, E, H, X, Z, Z, X, Z, W, right? It's going to be that simple. Won't be a problem, right? Yeah. No, it's a little bit more difficult than that. For a start, the cell could be set up in the opposite direction. The anode and the cathode could be switched. So that gives you a whole different set of letters. The other thing is that these questions will not be in the same order as they appear here. So you're going to have to be able to do it from scratch. Does anybody have any questions?
Yeah, I have one more. How is the electron flow determined again?
If we look at the things after we flip them,
Okay.
you can look at, hang on, I need to, yeah, I know you can't see my cursor on this side here, but I'm just going to circle this again. All right, so we've got the copper 2+ accepting electrons, and we've got the lead giving them up. By accepting, I mean the electrons are on the reactant side, and on the lead one, they're on the product side. Is that okay?
Yeah.
So what that means is the lead is giving up electrons, copper's accepting them. So when you look at the wire and you know which side the lead's on, you know the lead is giving up the electrons.
Giving out, okay.
And the copper 2+ is accepting them. But in order to accept them, they have to flow through the wire down into the copper.
Okay, that makes sense.
Okay. Any other questions? Okay. Let me show you some of the resources that we have for this. So in this folder down here, this is the galvanic cells folder, is what we're dealing with. Actually, I won't download it, I'll just view it here. So what I've got, the questions are all down below here, same as what we had earlier. And it's just a different setup than what we just had with regard to what the W, X, Y, and Z are. So W in this case is, in the first one, is titanium. It's in a solution of titanium 2+. The Z is nickel, and that's in a solution of nickel 2+. And from using the electrode potential tables and then going through the same process we just did, then we can come up with all of these different answers. And you see it varies depending upon what the anode and the cathode are. So I see this document here as being a good starting point for you to practice these. And the answers are there, so you can compare your answers and make sure you know what you're doing. The other thing that's good practice, I think, is the quiz. This galvanic cells qualifying quiz. Now, but the thing with this, I'll show it to you here, is you have to get 100% on it in order to get the credit quiz, but you can take it as many times as you like. See, it says unlimited. The catch is it doesn't tell you what the answers are. And the other thing is that these reduction potentials change as well as we go through the problems. So that's a bit of a catch as well. But you're answering the same questions we had to answer on the PowerPoint that we just went through. All right, let me explain what you're going to be doing here in this practice quiz, because it's very similar to what you do on the test as well. So I give you I, which is this imaginary element Q, and it's in a solution of QNO3, which is J. So that's always the way this goes. You've got a solid and it's in a solution. And I give you the reduction potential as being negative 0.459 volts. Now, how do you interpret that? Well, it's kind of similar. We've seen something like this before, believe it or not, when we were looking at the Nernst equation. If I'm telling you that the reduction potential for Q plus is negative 0.459 volts, what I'm saying is for this reaction, Q plus an electron gives Q, it's negative 0.459 volts. That's all it's saying. And for R plus, it's negative 0.923 volts. Now, how do I know the electrons are on that side? Because I'm saying it's a reduction. And reductions are always situations where the electron's on the reactant side. We know this from the reduction potential table because that's where all the electrons are in that as well. In this situation, does anybody know which one you'd have to flip in order to make the E naught positive?
The bottom.
Why do you say that, Alex?
It's bigger in number.
Oh, it's smaller. No, it's smaller. It's a smaller number. But you're right, it is the bottom one we flip, because what happens is that becomes negative 0.459 on the top, which is the same as what it was. But the R1 flips and becomes R plus an electron. And that becomes positive 0.923 volts. I think that's probably what you mean, is that when you flip it, it becomes bigger, right?
It's the only way to put the signs, the positive.
But the focus is on whatever is smaller initially, right? So whatever the smallest number is, that's the one you have to flip in order to get a positive E naught cell value. I don't care what the value is, but that's what you need to do. All right, does anybody have any questions? All right, so if you go through, you'll see you'll have different questions: nitrate flow, Q plus flow, etc. They're all multiple choice, but you don't get to credit quiz unless you get 100% on the qualifying quiz. And this is very similar to what you have to do on the test anyway. So I think it's really good practice. Plus, you get some extra credits. So. And is it really easy? No. Is it frustrating? Yeah, but it's good practice. So let's look at the problem on the test. You'll see how we go about it. Okay. So same kind of deal. And you see I've got this whole thing going here with the reduction potential. So you do have to write these down, and it becomes a matching type situation here. And these will vary. You know, these will vary in their order. So it won't always be in the same order. All right, does anybody have any questions? All right. Okay, any questions? Yeah, I did want to finish early today, but not too early. I've got a meeting at 9 o'clock. And what I'll do is I'll go through. Oh, I shouldn't have closed that. I'll go through this example here. It's in the test. Okay.
You just flip K.
Yeah, that's the one you'd have to flip. It's the smaller of the two, right? Yeah, so you'd have to flip K. But it won't always be K, but you have to flip. So in this case, yeah, you've got 0.5 volts. And we've got positive 0.10 volts. And just as we did, as I showed you in this one is the one you would flip. So it becomes negative 0.100. And that would be 0.5. And that gives us a positive value down here for our E naught cell. Does anybody have any questions? So based on that, then we can write down some things. We know that this is the reduction.
J is the reduction, and then K is the oxidation.
That's right. Yeah, through reduction, which makes that the cathode.
It'd be going.
And it's
The
plating.
direction of the electrons would be going to J, and then I'm assuming like the salts going the opposite way, so they'll be going to K.
The electrons, well, we'll get to that in a second. The other one here is the oxidation, which is the anode, which is dissolving. Does anybody need help with what I mean by plating and dissolving? Is everybody okay with that? Okay. So we'll do this in the order that we see it here. So the direction of flow of R plus. All right, so let's look at what R plus is doing. R is turning into R plus. That means it's dissolving here. So looking at what R is L. Hang on, let me shrink this a little bit. According to what we have here, R is L and K is R plus. So L is dissolving. So the direction of flow of the R plus will be H because the R is dissolving. It's turning into R plus. So that would be the answer there. The direction of flow of R would be H. And H is 8. See, it's in order, alphabetical order here. Always will be. Now the oxidizing agent. So the oxidizing agent, what's being oxidized is the R. The R is turning into R plus. What's causing that oxidation? Well, it's going to be the Q plus because it's accepting the electron that's being given up by the R. So Q plus is the oxidizing agent, and Q plus happens to be J, which is 10. Any questions about that? The reducing agent, what's being reduced? The R is being reduced to R plus. How's that? It's being reduced because, sorry, the reducing agent. What's causing the reduction? Did I get these mixed up? No, yes, yeah, sorry, Q plus is being reduced. Yeah, I've got that over here, all right. So what's causing the reduction? It's going to be the R by giving up the electron. So the reducing agent is R, and R is L, which is 12. Does anybody have any questions so far? The species being oxidized, the R is being oxidized to R plus. So that's going to be 12 as well. It's going to be R. The cathode is where there's the electrode at which oxidation is occurring, and that happens to be R as well, so that's going to be 12. Direction of electron flow. The electrons are flowing from the R to the Q plus. So from L over into J. So the direction of flow there is going to be A, which is going to be 1. The direction of flow of Q plus is plating. So Q plus is going to be turning into Q, which is going to be the I electrode here. So the direction of flow is E. Nitrate is flowing the opposite direction to where the electrons are flowing. So we know that the Q plus is turning into Q, the R is turning into R plus. That means the nitrates will flow from the Q side into the R side through the salt bridge. So the direction is D, which is going to be 4. The species being reduced is the Q plus. The Q plus is turning into Q, that's being reduced. So that's going to be J, which is 10. The anode is where oxidation is occurring, and that's going to be the Q, the actual metal there, and that's going to be the I, which is 9. So those are all the answers. That's how we submit it. So that's what you're going to be doing on the test. So again, I mean, practicing the test is going to be really helpful here as well. But the essence of all this is not in memorization. It's all in understanding what's going on in these processes. And as long as you understand that, there's nothing to memorize. Does anybody have any questions about this? Anything at all? All right, so what that does is it leaves us what's Thursday today. We got Tuesday and Thursday of next week where we're just going to be doing a review. And I would, nobody has any excuses now. I know that there's people out there that say, well, I'm not studying anything until we've gone through all the material. Well, look, we've gone through all the material. So there's no real excuse for saying, oh, well, I'm just going to wait. I'm going to wait to study. I'm going to wait till the last minute. Well, it's an option, but it's not the best option. I don't think it's worked I don't think it's worked well for some of you. So, and I mean, I don't really, honestly, I don't care how busy you are. I don't. You've signed up for this class. It's up to you. And it's all on you. I can't make you study. You've got to set aside the time and do it. All right, does anybody have any questions? Because I'm going to leave it here. Any questions? All right, if you need help, send me an email, call me, and my cell phone number's in the syllabus. We'll get any problem sorted out.
Thank you for your time, Professor.
No worries.
Have a good day and a good weekend.
Oh, thanks for coming, and I hope you get out of jury duty for good, Alex.
No, I got out of jury duty. Mine was at 7:30. That's why I'm here.
All right. Oh, excellent. That's good. All right. I'll see you all later.
See you later.
Thank you.
Bye.
All right. No worries. Thanks, Georgia.